Greetings. These are the videos, or the problems solved for Friday, September 23rd. These are coming from Chapter 7 of Gaskell. Okay, let's start with problem 7.1. And problem 7.1 reads, calculate the approximate pressure required to distill mercury at 100 degrees C, which is 373 K. Okay, so this is basically a problem in which we are going to be using the equilibrium pressure temperatures, which are in the appendix in the back of your book. And in fact, all of the problems in Chapter 7 are really problems focused on using that data set and using the Clausius-Clapeyron equations. So when you think about the quiz coming on Monday, focus on those as part of your studying. So we're looking at the approximate pressure to distill mercury, and we have the equilibrium temperature-pressure relation at the natural log of the pressure has the functional form of minus A over T plus B natural log T plus C, where A, B, C are fitting coefficients. In the case of mercury, the natural log of P is equal to minus 7,611 divided by T plus minus 0.795 natural log of T plus 17.168. Substituting in T equals 373 into here and here, we get the natural log of pressure is equal to minus 7.944, or the pressure is equal to 3.55 times 10 to the minus 4 atmosphere. Okay, next let's look at problem 7.2. Problem 7.2, we're talking about 1 mole of SiCl4 at 1 atm and 350 K, and we're told that it's in a rigid container with fixed volume, which means that we can determine the volume saying P1 equals 1 atm. Zoom out. Equals 1 atm. N1 is equal to 1 mole. T1 is equal to 350 Kelvin. Therefore, V1 is equal to nRT over P is equal to 1 times 8.21 times 10 to the minus 2 times 350 divided by 1 is equal to 28.7 liters. So that's the initial state of the system. And we're going to say that this container is going to be cooled to 280 Kelvin. And what temperature does the condensation begin? So for this, the number of moles is held constant. the volume is held constant because we have a rigid container with fixed walls. The temperature is going to change, and with that, the pressure changes. So P is equal to nRT over V is equal to 8.21 times 10 to the minus 2 over 28.7 liters times T is equal to 2.86 times 10 to the minus 3 T. So now we've got the pressure as a function of temperature, but then we also have the equilibrium relationship between pressure and temperature, and this is for SiCl4. And going to the table in the appendix of your book, we have that the natural log of the pressure is equal to minus 3.620 over T plus 10.96. So substituting in this, or I should say this for pressure, is going to give us a relationship entirely in terms of T. So we have natural log of 2.86 times 10 to the minus 3 T is equal to minus 3.620 over T plus 10.96. Solving for the temperature, we find that T is equal to 328 K. So that's the temperature where we see the first condensate. And continuing, we're supposed to find what fraction of the vapor as condensed when the temperature is at 280 K. So continuing with this, continuing with this, and using our expression for the equilibrium between temperature and pressure, and substituting in here 280 K, we get, I'm going to call this P final, is equal to EXP, so we're getting rid of the natural log, of minus 3.620 over 280 plus 10.96, or sorry, 98. 96 or 98? Should be 98, I guess. Sorry. 8 there. Is equal to 1.42 times 10 to the minus 1 ATM. So we have that. Let's work on problem 7.3 now. 7.3, in this they give you two equations expressing the equilibrium vapor pressure for a temperature, but they don't, and they tell you it's for zinc, but they don't tell you which one of the equations is for solid and which one is for liquid. So the question is, which of the two is for solid zinc? Now, one solution is to look in the back of your book because you have all the data, and that'll tell you which one it is. Another solution is to substitute some numbers and look at what comes out. So in particular, if we have, say, pressure versus temperature, at some point we're going to have some temperature where the two pressures are equal, And when that happens, we know that if we go slightly above, that we should wind up with a pressure for liquid which is lower than for solid. So let's do that. So in fact, we're just going to take and equate the natural log, so we can set this side and this equal to each other. So we can say minus 15,780 divided by t minus 0.755 natural log of t plus 19.25 is equal to minus 15,250 divided by t minus 1.255 natural log of t plus 21.79, and solving we get t equals 712K, or call it T star. Great, so that is the point where the two are equal. Let's go slightly above that. Test T equals 713K. And when we do that, the left-hand side of this equation turns out to be 3.929 times 10 to the minus 4 atmospheres. And the right-hand side turns out to be 3.924 times 10 to the minus 4 atmospheres, which is less. This is the liquid. And looking in the back of your book, we indeed find that this is the expression for the vapor pressure above liquid zinc. Okay, let's work on problem 7.4. Problem 7.4 asks at the normal boiling temperature of iron, which is 3,330 K, the rate of change of vapor pressure of liquid iron with temperature is this, or 3.72 times 10 to the minus 3 atmospheres per K. Calculate the molar latent heat of boiling of iron at 3,330 K. Well, you can probably tell from the wording of this problem, which is a little bit fictitious, that you're going to be working with the Clausius-Clapeyron equation, in which you have dP by dt is equal to P delta H over RT squared. In this case, we're doing this at presumably just standard operating pressures, 1 atm. That's the latent heat. Now we're interested in gas constant. That is going to be 3,330K. This is given in the problem. So we're solving delta H is equal to dP by dt times RT squared over P, or delta H is equal to 3.72 times 10 to the minus 3, that's atm per K, times 8.314 times 3330 squared divided by 1. Delta H is equal to 3.43 times 10 to the 5 joule per mole. That's problem 7.4. Okay, now let's look at problem 7.6. In 7.6, we're asked, we're given the molar volumes for the solid and the liquid of lead, and we're saying if we want to increase the melting temperature by 20 K, what do we have to do as far as changing the pressure? So this is going to be a problem in which we say we need this dP by dt, which again comes back to Clausius-Clapeyron over T delta V. Great. So to do this, we need to look up some numbers, in particular the latent heat of transformation. So at kind of standard 1 atmosphere, delta H is equal to 4810 joule per mole, and this is from the table in the back of your textbook. We have delta V is equal to 19.47 minus 8.92 is equal to 0.55, and this is in cubic centimeters. And we're going to be doing everything in liters. So this is cubic centimeter per mole. So that's going to be delta V is equal to 0.55 times 10 to the minus 3 liter per mole. Since there's 1,000 cubic centimeters per liter. So we got delta V, we got delta H, and the melting temperature of lead is 600 K. So putting these in to here, we get dP dt is equal to 4810, and look, this is joule per mole, and we're dealing with pressure and volume in terms of liters, so this has to be divided by 101 to convert from joule to liter atmosphere. Divided by 600 times 0.55 times 10 to the minus 3, or dP by dt is equal to 144 atm per K. And we'll treat that as constant. It's not really, but it's pretty close to. There'll be small deviations with small changes, and 20 degrees is not a big change. 20 degrees out of 600, so we can treat this as constant, which means that now we have delta T, so we can say delta P is equal to 144 times delta T 20, or delta P is equal to 0.2880 atm. So that's the change in pressure necessary to increase the temperature by 20 degrees. So now let's look at problem 7.8 from Gaskell. So this problem asks us, says, given the saturated vapor pressure of liquid neodymium chlorine at 0.3 atm at 478 and a pressure of 0.93 atm at 520 K, calculate the normal boiling temperature. So this problem is really about you getting a good approximation for the expression natural log P is equal to A 1 over T plus B natural log T plus C. The challenge here, though, is that you're only given two points. So you have to decide how you're going to approach this, and looking at it, right now you know that this constant, that's probably going to be important. These, because that gives you an absolute rigid offset. These, though, which one's important? So the way I approach the problem is I first solved for natural log P is equal to A 1 over T plus C, and then I solved for natural log P is equal to B natural log T plus C. And I thought I would test the two and see how well they operated. So, doing this first problem, say natural log of 0.3045 is equal to A 1 over 478 plus C, and natural log 0.9310 is equal to A 1 over 520 plus C, and that gives you A is equal to minus 6614, C is equal to 12.648. Going over to problem 2, we're solving natural log of 0.3045 is equal to B natural log 478 plus C, and natural log of 0.9310 is equal to B natural log 520 plus C. Solving these together, we get B is equal to 13.2702 and C is equal to minus 83.0604. Substituting these into natural log of 1 is equal to minus 6614 over T plus 12.648, we get T melting is equal to 523 K. On the right hand side, natural log of 1 is equal to 13.2702 natural log T minus 83.0604. T melting is equal to 523 K. So it turns out that either one of these expressions can be used to give you the same melting temperature. We feel pretty good about that. So this is problem 7.8.